So we have a GRE Physics practice, 12 problem set. I'm going to skip over 26. 26 is 4A. I'm going to go over 26 on the next page just because it's in more detail with the steps. I'm going to start with 27 here. But if you want to go ahead and do 26, it's 4A downward. 27, two simple pendulums, X and Y, consist of masses that are equivalent and suspended from strings of length L sub X and L sub Y, respectively. The two simple pendulums are oscillating in identical gravitational fields. If the period of simple pendulum A is 16 times the period of simple pendulum B, what is an equation that could represent the lengths of the two simple pendulums? So we have a simple pendulum problem, and we could say rather RT is going to be proportional to the square root of L. So if we set up T sub A over T sub B, that's going to wind up being the square root of 4x over y. That's going to be set equal to 16 over 1, or 16. If we square both sides, we get 4x over y is 256. And we could write x in terms of y. X would be 64y. So that's an equation that could represent the lengths of the two simple pendulums. For these, unlike a regular GRE, for these, we don't have an A, B, C, D, and E. They're from scratch, pre-response. For 28, what would be the rest mass of a particle with total energy 8.0 GeV and momentum 7.6 GeVC? So E squared is going to be equal to PC squared plus M naught C squared squared. So we need that formula. And this M naught C squared, that's going to be equal to the square root of 8.0 squared minus 7.6 squared. That minus that, this squared minus that squared. You're probably very familiar with that. Square root is 6.24. That gives you 2.5. Whoops, a daisy. Very, very sorry. Very sorry. Old-fashioned setup here. So that's going to give us square root of 6.4, 2.50 GeV. So M naught is 2.5 GeV C squared. So that's 27, that's 28. Let's do 26, and I'm going to turn the page to do 26. For the circuit shown in the figure below, what is the current? Okay, what is the current I through 12 ohm through the 12 ohm resistor? So this is the diagram we're dealing with. So if you just want to get that diagram down, I'm going to show this in 6 steps, just in case you need review. You might have already got it. So just wanted to show this in complete steps. So step 1, what we do is we combine the parallel resistors, the 6 ohms and the 12 ohms. And what we do, that the parallel resistors, we take their product, 6 times 12 over their sum, 6 plus 12, 72 over 18, that's 4 ohms. Step 2, we want to find the total resistance. So this 4 ohm equivalent resistance is in a series with the other 6 ohm resistor. So we're going to get the R subtotal. 6 plus 4 gives us our 10 ohms. Step 3, we're going to find the total current. Total current is V over R total. So that's going to be 120 over 10. So that gives us our 12A, 12 amperes. Step 4, we find the voltage drop across the first 6, the 6 ohm resistor rather. So that's going to be V equals IR. V equals 12 times 6, and V is, that's going to be 72. So we're going to get 72 here, all right? So for step 5, we want to find the voltage across the parallel branch. So we're going to take our 120, that was the given volts, minus, on the previous page, 120 was the given amount of volts, minus the 72. That's going to give us a leftover of 48 volts. So the 12 ohms resistor has 48 volts across it. So we're ready for the final step. Find the current through the 12 ohm resistor. Well, I equals V over R. I equals the 48 over 12, and it gives us 4 amperes in the downward direction, 4A downward. Okay, so that's 26. I just wanted to show it in the steps just in case. Okay, moving along. Moving along, that was 26, 27, 28. Okay, so 29. Okay, 29, an ambulance driver hears an echo of the ambulance's siren from a wall toward which the ambulance is moving with a velocity of 4.8 meters per second. The frequency of the siren is 750 hertz. Approximate the echo's frequency that the driver hears. So the echo is coming from the wall. F prime we're going to use is equal to F over V plus V sub S over V minus V sub S. Okay, so our V, 343 meters per second, and our V sub S is 4.8 meters per second. So 343 plus 4.8 over 343 minus 4.8. Well, when we reduce that, we're going to get 771 hertz. Okay, so, and some people might use a different notation for these, for the V and the V sub S. But here's the setup, 771 hertz. Okay, so 30. Two objects slide on a frictionless surface in a state as shown below. The objects collide and stick together. How much kinetic energy is converted to heat during the collision? So here we have our XY. So we have from this object going 4 meters per second, 80 kilograms. This object's going 20 meters per second. It's 20 kilograms. They're going to collide. So we get our initial kinetic energy, K sub I. That's going to be 1/2 times 20 squared plus 1/2 times 80 times 4 squared. Okay, initial kinetic energy. That's going to be 4,640 joules. Our momentum, P sub X, 400. And our momentum here, P sub Y, is going to be 320. Okay, when we multiply mass times velocities respectively. And then our final kinetic energy is, let's see how we're going to get that. Well, final kinetic energy, K sub F, we're going to have this P squared over 2M. That's going to be 400 squared plus 320 squared over 2 times 100. That's going to give 1,312 joules. So we're being asked about how much kinetic energy is converted to heat during the collision. So the heat lost is going to be K sub I minus K sub F. So it's going to be 4640 minus 1312. And we're going to get 3,328 joules. Okay, and I apologize if I'm going very fast, but you can always pause the video, try these problems on your own. Never trust me fully, always verify. Because I could go too fast, who knows. 31. There could always be a mistake made here and there. A refracting telescope consists of 2 converging lenses separated by 500 centimeters. The focal length of the eyepiece lens is 60 centimeters. What is the angular magnification of the telescope? Okay, so optics. Telescope length, F naught plus F sub E. That's going to be equal to 500 centimeters. F naught in this situation, 500 minus 60, that gives you 440 centimeters. So angular magnification, that capital M is going to be negative F naught divided by F sub E. That's negative 440 over 60. We get negative 7.3. And our our magnitude, sorry for the misspelling there, our magnitude is 7.3. Yeah, that should be... That kind of made it worse, but magnitude 7.3, you get the picture. So that's 31. Moving along, 32, 33, 34. Okay, so these, if a charge Q for 32, if a positive Q is located in M units at the point 4718, what is the total electric flux that passes through the XY plane? Okay, so here's the flux formula through an infinite XY plane. Q over 2 epsilon naught. Now here's the situation here. Conceptually, this point where it's located, think about which octant this is located in. And with an upward normal. Since this charge is above the xy plane, okay, what's going to happen with the charge is it would be negative. So I wrote this twice because this one came out a little sloppy. So the charge is equal to negative q over 2 epsilon naught. Number 33, an arbitrary photon detector has a quantum efficiency, I should have said, of 0.12. If 800 photons are sent into the detector in sequence, one after another, how many photons will the detector detect? Okay, so expected photons detected, that n would just be equal to the product of the 0.12 in the 800. We get 96. 34, a grating spectrometer approximately resolves two wavelengths of 880 nanometers and 884 nanometers, respectively. What is the resolving power of the spectrometer? So resolving power is going to be R equals lambda over the change in lambda. To get lambda, we take the average of the two quantities given of those wavelengths. Taking their average, we get 882. So for lambda, we use 882 over the difference between them, 884 minus 80. So 882 over 4, that gives you 220.5. And if you want to approximate, round up, 221. So that would be the resolving power of the spectrometer. So that's the 32, 33, 34. And now we go to the last three. Okay, so, whoops. Okay, 35. A particle has spin 0 and mass m. It is in 3D. It is in a 3D isotropic and is described by this. V of r equals 1/2 m omega squared r squared, where x squared plus y squared plus z squared is r squared. An energy of 39 over 2 h bar omega represents how many states? Okay, so 3D harmonic oscillator. Our E is equal to quantity n plus 3/2 times h bar omega. Now, if we just solved for this, set 39 over 2 equal to n plus 3 over 2, we get n is 18. Now, what we want is the degeneracy here in this problem. So G equals n plus 1 quantity times the quantity n plus 2. Taking that and dividing it by 2, we just get 19 times 20 divided by 2. We get 190 states. And 36, a magnetic field is directed perpendicular to the plane of a coil that is circular with an area. This should be an area, sorry about that. Should be area of 0.9 meters squared and 405 turns. The magnetic field is then increased from 0.037 Teslas to 0.057 Teslas, these T's, capital T's, Teslas, during a time interval of 0.8 per second. What is the induced mean EMF in the coil? Okay, so we're looking for the average here. This is off of Faraday's law. And we could say this modulus, this absolute value of epsilon here, equals NA times the change in B over the change in T. Change in B being the magnetic field here, so change in the magnetic field. So N is 405, A is 0.9. Denominator is going to be 0.80, the time, and then the numerator is going to be the difference between the two Tesla values we were given. And we're just going to wind up with 9.11. All right, so that is the induced mean EMF, 9.11 there. And number 37, the drone drops a payload while traveling due south, while it is parallel to the Earth, traveling at a velocity of 130 meters per second, neglecting air resistance. What is the velocity of the ejection in relation to the drone? 11.0 seconds after the release. Okay, so let's see here. This was a different problem originally. I'm just going to cross this out. Sorry about that. Okay, So, my apologies for that. My apologies for that. So, here, if we get v sub y first, that's g times t. That's going to be 9.8, our gravity, times 11.0, our seconds. So that's going to give us approximately 107.8, actually, yeah, 107.8 meters per second. If you wanted to approximate 108 meters per second, okay, in the downward direction. However, our velocity here, okay, in the horizontal direction was given as 130 meters per second. So we have 130 and 108 for v sub x and v sub y respectively. So if we take the magnitude of that for the velocity, so v equals the square root of 130 square root of 130 squared plus 107.8 squared, and we're going to get approximately for our answer 168.9 meters per second. Okay, so I went through that pretty quickly. Remember always to verify, never trust. Check your answers if you go through this, and thank you very much. And I'm going to keep this, try to do hundreds of these over the course of the next however time. Just because it's good for review for undergraduate physics, and it's good in general because almost everyone, not everyone, but almost everyone tends to forget a lot of stuff over time. So it's good to review these type of problems. All right. Well, hope this helped a little bit. Hope it was kind of fun for doing some physics problems, and have a great day.